now we will study the mechanics of rocket propulsion using Lagrangian and Hamiltonian equations. Let us start with Lagrangian equation. We know that the kinetic energy of a system is given by half mv square, but first let us start with analyzing the system. So we are considering a rocket which is moving away from Earth. Let us take the height of the rocket, or the coordinates or position vector of the rocket, as q, and its derivative with respect to time as q dot. These are the generalized coordinate notations that we use. So now our kinetic energy will be half mv square or half mq dot square, and our potential energy is mgq or mgh, depending on whatever notation you use. The Lagrangian energy of a system is defined as kinetic energy minus potential energy, so k minus u. So it's half m q dot square minus mgq. We know that the equation to use for Lagrangian mechanics is d by dt of dou L by dou q dot minus dou L by dou q is equal to 0. So let us calculate the values and substitute. Now when you calculate dou L by dou q dot for this k minus u, you see that only this term depends on q dot, so you will get mq dot, because 2 and 2 will get cancelled. And when you calculate dou L by dou q, since only this term depends on q, you will get minus mg. Substituting these in the equation above, you will get d by dt of mq dot plus mg is equal to 0, dou by dt. So then since m and q dot both depend on time, so using the multiplication property of derivatives, you will first write m q double dot plus dou m by dou t q dot is equal to minus mg. And this is our equation of motion using Lagrangian. Now let us use the Hamiltonian approach. The Hamiltonian energy of a system is kinetic energy plus potential energy. So the Hamiltonian is calculated as half m q dot square plus mgq. The Hamiltonian equations that we use here are dp by dt is equal to minus dou h by dou q or minus dou h by dou r. Q represents our coordinates, and dr by dt is equal to dou h by dou p. Here p is our momentum. But here your momentum can be calculated as dou L by dou q dot. So it's nothing but mq dot, which we calculated in the previous instance. Or you can simply consider p is equal to mv, so it's nothing but mq dot. Now substituting this in our first equation, you will get dou by dou t of mq dot is equal to minus of dou h by dou q, which is nothing but minus of mg. Because if you derive this with respect to q, if you differentiate it with respect to q, then only this term depends. So then finally, plugging in all your values, you will get mq double dot plus dou m by dou t, because mass also varies. Because as a rocket travels, it expels gases with constant velocity and sometimes even ejects components. So mass varies, so dou m by dou t into q dot is equal to minus mg. Actually, if we verify, we see that we got the same equation using both Hamiltonian and Lagrangian, which is a proof that our equation is valid.